Fusion Mobile, quality e-learning experience on the go.
Welcome to Fusion Mobile e-learning clinic. My name is Sonia Lalawa and I'll be walking you through the physics course. Now we want to consider waves. And in this topic of waves, we'll be looking at the definition, we'll consider in the topic what is wave. We'll look at wave motion. And we'll also consider transverse and longitudinal waves. We'll talk about propagation of waves, the general representation of a wave, the terminologies used in the discussion of waves. That is, terminologies used in the calculation that has to do with waves. Then we'll consider the equation of a traveling wave, wavefronts, progressive and stationary waves, properties or characteristics of waves, and we'll conclude the lesson with polarization of waves. So, what is a wave? A wave is any disturbance that transmits energy. A wave is any disturbance that passes through a particular medium and has the capacity to transmit energy from one point to another. A wave is any disturbance that passes through a medium and has the capacity to transmit energy from one point to another. Let's take, for example, different kinds of waves we do see. If you get a stone, if you have a stone in your hand and you throw it into a bowl of water, you'll see ripples coming out, forming a kind of an identical shape with the stone. That is the outside shape of the stone. That, what you're seeing there, is a wave. Is a kind of wave. So there are many kinds of waves we can see. You can, if you have your like you see children play with skipping ropes. They have a rope, two people holding the rope at two different ends, and they turn this rope. The rope forms a kind of semicircle moving. It is a kind of a wave. In a few seconds, some questions will pop up on your screen. Please answer them. We want to see what you've understood so far and what has been taught. Let's talk about wave motion. When we consider wave motion, we're talking about how do waves move. Basically, waves move from the point of generation outward towards other places. And if we study the motion of waves, especially the ones that we can see with our eyes, those are the mechanical waves. You observe that waves move in a kind of circular path, a kind of a circular path, a semicircular path, in an oscillatory manner. So let's look at the types of waves we have. We have two kinds of waves. These two kinds of waves are the mechanical waves and the electromagnetic waves. Mechanical waves and electromagnetic waves. But these two waves also can be further broken down into what we know as the transverse wave and the longitudinal waves. Transverse waves and the longitudinal waves. Now, for the transverse wave, what happens is the source of the wave, that is the source of the disturbance, is perpendicular to the direction of the wave. In other words, when you throw your stone vertically into water, the ripples do not go down, rather they spread away. So it forms an angle of 90 across the surface, as in the point of contact, point of initiation, the source of the wave is perpendicular to the direction in which the wave moves. That's why we call them transverse waves. And the longitudinal waves, the source of the wave is in the same direction. It is in a parallel direction with the wave. In other words, a very good example of longitudinal wave is sound. If I should turn my back and speak, my voice goes in more towards that direction rather than going downward or upward. Though yes, it goes in all those directions, but more in the direction in which it is being sent. So that's transverse waves and longitudinal waves. To represent transverse waves, we usually use the waveform diagram, where we have oscillatory motion, and to represent longitudinal waves, we use lines, because it depicts more of what is actually happening. The waves come out and move like that. The waves come out and move like that, following the source. The way the source releases it out, it follows that same parallel direction and it progresses. We've considered wave motion and we've spoken of transverse and longitudinal waves. Okay, let's look at propagation of waves. Propagation of waves. How are waves generated? Well, waves are generated via using different sources. Especially when it comes to propagation of waves, we consider more of the definition of the splitting of the waves into mechanical and electromagnetic waves. The difference between mechanical and electromagnetic waves is very simple. Mechanical waves always need a medium for them to be transmitted, but electromagnetic waves do not need medium to transmit them. They can move through even the vacuum. A very good example of an electromagnetic wave is light. The light reaches us from the sun without passing through any medium. That is, it passes through vacuum and it still gets to the earth. But your sound is if there is no medium such as air, your sound cannot be transmitted. So when it comes to waves, the mechanical waves always need a medium, but the electromagnetic waves do not necessarily need a medium. A medium can be an added advantage. So, spoken of that. General representation of a wave. General representation of a wave. Generally, we represent waves using this waveform that I drew up here and I described as the manner in which transverse waves do move. We use them to represent both transverse and longitudinal waves. And why do we do that? Is because even in the longitudinal waves, they can kind of represent your diagram to suit something like this. In your transverse waves, there are some points that are very, very important. Of course, one of them is this location known as the origin. And this point up here, the highest peak is known as the crest, while the lowest depth is known as the trough. Also, the distance between one crest, two successive crests, that is one crest and the immediate next crest, or one trough and the immediate next trough, is known as the wavelength. It is represented with the symbol lambda. So, if we want to translate what we have here, what we have in this particular system is we have compression and refractions. Compressions and refractions. We'll get to some places we have a lot of very tightly packed, and as you go on, becomes spaced, and then becomes tightly packed again, and then spaced. So our compression points can represent our points of crests, while our refraction points can represent our points of troughs. So when we kind of if we try to observe the compressions and refractions in time, of course, everything but the wave is always drawn on as distance against time. That's what we're always using to draw our graph. It's a distance time graph. So when you represent it in distance and time, then you would have something like this. So we always draw our waveforms, we always use this in explaining our waves as our wave diagram. Okay, let's take some terminologies, terms that we would come across in our study of waves. One of the most important terminology is what we call the wavelength. The wavelength. It's represented with lambda, and it is defined as the distance between two successive crests in a particular wave diagram. It is the distance between two successive crests in a wave diagram. We also have what we know as the amplitude. Represented with A. The amplitude is the highest distance, the highest vertical distance, that's the highest displacement that the wave makes, is the highest displacement that the wave causes or the wave makes. So the amplitude is, you pick your crest and you pick it out, or you can just take it from here. That's the amplitude. That's our amplitude. It's the vertical distance. Now, we'll talk about period. Period is represented with a capital T. The period is the time taken for a wave to perform a complete oscillation. The time taken for a wave to perform a complete oscillation. And what do we mean by a complete oscillation? A complete oscillation can be from origin source through the crest and the trough back to the origin source, or from the first crest to the next crest, or from the trough point to the trough point. The point is, it must complete a circle. The circle must be complete. The starting point must also be a replica or an identical point of the ending point. The ending point must be an identical point of the starting point. So it must appear as though you have moved a complete circle. That's a period. And yes, our wavelength is measured in meters. Amplitude is also measured in meters. Period is measured in seconds. And we have frequency. Frequency, which goes with F. The frequency is the number of oscillations, number of complete oscillations that a wave performs in a unit time. Number of complete oscillation that a wave performs in a unit time. And the unit time we do use is seconds. So frequency is measured in hertz. Frequency is measured in hertz. How about considering one or two relationships that can be drawn from the old equations, from the terminologies that have been stated, that have been listed? Okay, let's consider. We said we have our.
Say that again. Let's consider.
I don't want to consider again. We have said our diagram, our graph represents the distance time graph. It's a distance time graph, that is, shows the relationship between distance and time. And of course, whatever comes between distance and time has something to do with velocity. It has something to do with velocity. So that brings us to talking about velocity. And velocity can be spoken of in this area in waves in form of angular velocity and velocity. I don't want to use the word actual velocity because let me just say actual velocity and angular velocity. The actual velocity is just simply described as velocity and it is represented with v, while angular velocity is represented with omega. We have our velocity, and we know velocity is the rate of change of the time rate of change of displacement. Velocity is the time rate of change of displacement. Velocity is measured in meters per second, and angular velocity is measured in radians per second. Is measured in radians per second. Angular velocity is the time rate of change of angular displacement with time. It is the time rate of change of angular displacement. It is the time rate of change of angular displacement. Putting some of these things into use, we can always calculate our velocity. Velocity can be calculated as distance divided by time, and distance here we have our lambda, which is our wavelength, divided by time. Here we consider time as period. So our velocity is lambda divided by time. Also, to note, something very important to note is I describe frequency. We describe frequency as the number of complete oscillations made per unit time, and we described period as the the time taken to make one complete oscillation. If you are observant, you would realize that the relationship between period and frequency is going to be an inverse one. In other words, frequency and period should be equal to 1 over frequency. So we have that expression also that holds. Period equals to the reciprocal of frequency. And if that is so, it would also mean that frequency is the reciprocal of period. Thus, the v, that is velocity here, equals to lambda multiplied by frequency. So these are the terminologies that we will work with when it comes to the wave equation. Prior to this lesson, we considered simple harmonic motion, and we established the relationship that exists between a circular motion and a simple harmonic motion. And of course, we add the waveform of simple harmonic motion, just like what we have here in our own observation of waves. Today, we want to also consider the different equations that we could have for a waveform. A wave can take up different. We have different kinds of wave equations that we could have. Basically, two. When the wave starts from the origin, it goes with y equals sine theta, because when you plot it, the way our y is our vertical axis. I want to blow up this diagram. When you plot it, you have something like this. So you look at it, you actually find yourself working in a kind of a triangle, and we're considering our height. So the angle here is the theta. So it is in the opposite direction. So if this is our hypotenuse, this is our hypotenuse, this is the opposite, and the relationship between hypotenuse and opposite can be found rather in sine of angles. It can be found in sines of angles. So y equals to sine theta. But in another case, in the case of when the wave equation, this is drawn as this. When the wave curve is drawn in such a case as this, we see it coming up in a different way, and these ones go with y equals cosine theta. Why cosine? Because we have to now project our diagram and come something like this, and we'll have to transfer our theta would no longer act as a theta, rather it will be acting from the angle from 90 minus theta, because what we ought to measure is the forward one, but then what we can measure is a backward one. So we have to take 90 out of theta, and of course sine theta minus 90 will give us cos theta. Sine 90 minus theta, that is sine 90 minus theta, when this is inside bracket, it will give us cos theta. So we'll have to first take out the 90 degrees which has been reached here before we can start our calculation. Instead of us going, the new angle is supposed to be the old angle here. So the expression stands. Now this expression, this is a trigonometric derivative. If you press your calculator, you can get your calculator and press on your calculator, you check for the sine of 30 degrees. You find out that the sine of 30 degrees is equal to the cosine of 60 degrees, and 90 minus 30 gives us 60. If you do sine 20 and you check for cos 70, you find them to be also equal to each other. So that's how we confirm that switching. Now this 90, of course, I explained, it's coming from the fact that half of the wave has disappeared. So it has traveled a distance, but we are taking our measurement from this particular distance. So that distance that it has traveled must be taken into consideration. If we want to indicate this on a proper wave, we'll put here at the midpoint pi, at the end point 2 pi, of course. 2 pi equals to a full circle. The circumference of a circle is 2 pi r, and r is always ignored when it comes to this. So this place would be 3 over 2 pi, while this point would be pi over 2. And as we know from trigonometry, pi is always representing 180 degrees in radians. So when we say half, it means, when we say half pi, it means 180 divided by 2, which is 90. And that's how we came about this 90 that we're subtracting the theta from. Alright. To press further, still on equations of traveling waves. It's not all the time that you will start from either the crest or the origin. Some other times you can start from another point which is neither crest, origin, or trough. Maybe a particular curve as this. Let's stop it here. Maybe another one as this. In this particular case, in this particular case, we have to take note of where this would have landed, and of course we will take note of our theta, and we'll take the measurement of what is there and we'll take it as phi. We'll take it as phi. So in this kind of condition, we have an expression, a more complex expression as sine theta, sine into bracket theta minus phi. Of course, the other time we considered our phi was close to 90, it was about 90. Of course, our theta cannot be as big as 90. Our theta is not up to 90, so we have to, but this time around it is smaller than 90, so, and our theta must be bigger than our phi. So we use the expression theta minus phi. But then, from simple harmonic motion, we know that our omega equal to theta divided by time. Our omega equals to theta divided by time, and time here, of course, every time we're considering time here, we're talking about period. So we can easily represent our theta as mu. Okay, let's stick with time, because we have different times in the curve. Mu omega t. So we can have this expression here as sine omega t minus phi. The same thing we can have here, our expression will now be sine omega t, and this one will be cosine omega t. I know it's getting more and more complex, but it will soon begin to make a lot more sense to us. Now, our file itself can also be simplified because it is an angle and it is a distance that has been covered through a particular angle. So to get the actual value of what that particular distance is, we can go ahead and calculate. We can go ahead and calculate. This theta is measured based on the file is measured based on the distance between the starting point and the supposed to be the place the wave is supposed to start from, and the place that is pointed as our origin. So the measurement will be taken as x, and that's, we can calculate our file by 2 pi x over r. We can calculate our file as 2 pi x over lambda. So we can take this and use it to replace that, and we'll get to see what we usually see as most of the time as our waveform equation, which is sine omega t minus 2 pi x over lambda. So this is what we usually generalize as our waveform equation. No matter what, your x may be equal to 0. If x equals to 0, this whole expression will disappear, and we'll have sine omega t. Our x can be as high as half of the original of the lambda. Our f can be half of lambda, and when x is half of lambda, that means we'll have 2 down here and lambda up. Lambda will cancel out lambda, 2 will cancel out 2. Then we'll be left with this minus pi, and that will give an expression. Of course, you can never subtract whatever it is. Pi is 180. It will give an expression of cos. It gives an expression of cos. That's because you have to start changing the planes. Let's not dig too far into that, because it might get a bit confusing if your knowledge of trigonometry is not very sound. But let's take an example. Maybe it should shed more light on it, on how we can apply these equations in the examination. Alright, let's consider this particular question we have on the board here. A traveling wave on a string, is given by the expression y equals 0.03 sine into bracket 2.2x minus 3.5t close bracket, where x and y are in meters. Find the amplitude, frequency, period, and speed of the wave. Alright, let's see what we can do about it. Well, the first thing I would recommend you do is to copy out the equation given to you in the question. That is y equals 0.03 sine into bracket 2.2x minus 3.5t. And then you should choose a suiting wave equation. A suiting wave equation that should accompanying this is y equals a sine into bracket omega t minus kx. Yes. Now our a, of course, is amplitude. So we're asked to find amplitude. We can easily pick out our amplitude. A equals 0.03 meters. Of course, when everything starts attracting each other, the sine attracts the sine. This and this go together. Omega, so that means our omega a, that's our angular speed. Omega a will be 3.5. Omega equals to 3.5. And k here will be equal to 2.2, but we don't need that in this question so far. Of course, 3.5 radians per second. So, what else? What are we asked to find? We're asked to find the frequency. From this, we can calculate out our frequency. We can calculate out our frequency by using the expression frequency equals to omega divided by 2 pi. So our frequency will be given by 3.5 over 2 pi. When you calculate that, that will be 1.75 over pi. At 1.75 over pi at. Okay, we're also required to calculate the period. The period. We know our period is always equal to the inverse of our frequency. So you can say period equals to 1 over frequency, which equals to 1 over 1 divided by 1.75 over pi. That would give us pi over 1.75, and that was, of course, in seconds. That will be our period. And the speed of the wave. Speed of the wave, that's velocity of the wave. You can finish up these calculations, the one for the frequency and the one for the period, by using the value of pi. Of course, I'm sure we all know the value of pi as 3.14. So you can use 3.142, or you use 3.14, or use 22 over 7, whichever one you do know how to work with. To calculate our speed, the speed, we know that speed v equals to length. In this case, our length is wavelength multiplied by frequency, or length divided by the period. So how do we get our wavelength? This constant, this wave constant k, it is equal to 2 pi over lambda. 2 pi over lambda. That's what that k equals. So we can take out that k, which is 2.2. So our lambda will be equal to 2 pi over k, which is 2 pi divided by 2.2. So we can import that into this particular expression. We have our value for frequency. I would like to work with frequency and lambda. Working with frequency and lambda, I have my lambda as 2 pi divided by 2.2, multiplying my frequency is 1.75 divided by lambda. Lambda will cancel out lambda. 2 can go here, 1.1 to here, 1. 1.1 can go here, 1, and we can have here 1.6 plus 1.59. So our velocity is 1.59 meters per second. Approximately 1.6 meters per second. So this is how we solve the questions when it has to do with waves. You first write out your wave equation, the one that is most appropriate with the question you are trying to solve. If you have ones that have your pi immediately after your sign, or maybe it has a value immediately after the sign before the brackets, then you know that your k has been brought out. And in that case where your k has been brought out, it simply means that your wave equation equals y equals a sine k into bracket vt minus x. Of course, your v is velocity, the velocity of the wave. It looks like u. Let me make it look like v more. Yes, you can use that. Now your k, of course, your k always has the expression 2 pi over lambda. 2 pi over lambda is always the k. So sometimes you may not even see k there. You may just see, maybe they will write 2 pi over lambda, or maybe they'll put a particular value. What they are trying to communicate is they are giving you your lambda. So it's all about you being able to identify from the expression you are given which of the equations to use. Okay, we've spoken of equations on traveling waves. Okay, let's quickly talk about wavefronts. Wavefronts. What do we mean when we talk about wavefronts? Wavefront simply talks about the description of the appearance of the waves, the appearance of a wave. For example, if a wave is originating from a round stone or a spherical stone or a ball that was dropped in water, something circular, the wave form, that is kind of shape of the wave, would be circular and to keep growing. So this is the waveform. But there is also the one for the plane substances. That's the wavefront. Now, in the case of planar substances or planar shapes, a log of wood, when you drop it into the water, you notice that it has something like this. Around the edges, there is a curve. That's what the wavefront looks like. Instead of this one that will just be going roundish, it one goes more of literally then around the edges. it takes the round shape. So that's what we'll look at, what we're talking of when we talk about wavefronts, the appearance of the wave that come out due to the shape of the source. Okay, let's talk about progressive and stationary waves. Progressive and stationary waves. Of course, when we talk about progressive waves, it means the wave is advancing, it is progressing, it is moving. And when we talk about stationary waves are waves that are originating from two fixed points, or rather originated between two fixed points. Their operations is restricted to just those two fixed points. So in stationary waves, a very good example of a system of stationary waves is your guitar, that is your playing instruments. Your guitar, which is an instrument, a musical instrument. The guitar is designed such that at two ends a string is tied, fixed, stationary. But when the string is pulled, it oscillates and vibrates, and then it gives something like this. Of course, one at a time. But that vibration, that is what is described as, that's what brings about the phenomena of the stationary wave. Now, stationary waves are two different waves. There are two waves, two identical waves, acting together in a system. They are moving in opposite direction. And normally, if not for friction, it should continue like that forever. There are some calculations that will do some little. There are some things that we need to take note of when we talk of stationary waves. One of the two of them, we have two of them. We have two different locations on a stationary wave. Those are the fixed points where the amplitude of the wave equals 0 or equals to the average. It is equal to 0 when you have a positive and negative, but it is equal to the average when you don't. It is not a positive and negative. The whole thing falls under positive, or everything falls under negative, or it mixes but not in the middle. Now, these our fixed points are called the nodes. And the place or region where we have the maximum amplitude, that is the extreme, which actually finds its way somewhere in the center of two nodes, is what we call the antinode. Antinodes. So in every stationary wave you find nodes and antinodes. So in your pipe organ, your stationary waves is also present. Yeah, it's one of the reasons why we hear those kind of music, those kind of sound that come out of it. And we also use the knowledge of this in designing systems where we want our waves to be consistent, to be sustained, or to be removed. Because stationary waves actually keeps the whole thing going. If you are playing if you are a guitarist, you play your guitar or a string instrument, as you play, you observe that when your hand leaves the string, the sound coming from it tends to change. Yes, that's because the stationary wave has been reduced, has been changed, has been relocated. You have removed the node from where it used to be, and a new antinode has been formed. Let's talk about the characteristics of waves. what are those features that waves possess? And we are able to say, wow, this is a wave and this is not a wave. Well, waves generally have about 4 different characteristics that distinguish them from other things. And the first one is described as reflection. Reflection. A mirror and a light. You take your mirror and you put it, and you can actually use it to control the light and move the light to a specific direction. That is reflection. The light shines on the mirror and shines away to another location. A wave can be reflected. It can be controlled. You can use a reflector to send it to another direction, to redirect the light or the wave. So apart from reflection, we also have other things as refraction. Refraction. Unlike reflection, where you turn away the light to somewhere else. In refraction, a wave is moving with a particular speed and wavelength, and then it makes contact with another body. Probably the wave is moving in light, in air, as we have. Let's use light now. I want to use light as an example. You on your torchlight, and your torchlight is moving in air, and maybe for some reason it has to enter into a swimming pool. You notice that it looks like the light actually bends and moves somehow further forward. Meanwhile, it's not. You are not pointing it like that much forward. For example, let me try to give a. If you're standing by a pool, and someone is inside the pool, and you're looking into the pool, it will look as though, even though when you're told that this pool is 5 meters deep, you'll be looking inside the pool, and instead of you seeing 5 meters deep, you'll be seeing probably 3 meters deep. It will be looking like it's not as deep as it is said to be. This is due to refraction. Refraction occurs when there is a change in medium through which a particular wave is passing. And we'll be looking deeper into reflection in our next topic. The next one to consider is known as diffraction. Diffraction. In diffraction, we see a particular wave going on its own, and then you set up some form of barricade. And when the waves manage to come out through the barricade, they try to go back to spreading and moving, they try to go back to moving the way they used to move before entering into that barricade. That's diffraction. It tries to move as it was moving before. In fact, probably even now start spreading more. You observe this better when you use water as an example. You take water and you have a funnel. Maybe you are putting water through the narrow end of a funnel. You notice that when water enters the bigger part of the funnel, it will actually spread out to occupy more space. That's the nature of waves. They diffract. And also, there is the status of interference. Interference. Let me check spelling. Single R. There is also the status of interference. In interference, it is possible that two waves are moving and they merge into each other. Yes, but for this to occur, they must have been moving at the same frequency. Now, if they are moving at different, how do you think they do it that you speak into a particular device and your voice comes out louder? Or let me use a clearer, a very much easier to understand concept. That's listen to a church choir. Everybody singing at his or her own crescendo, or at each of our own pitch. And then you see everybody singing, the baritone blends with the alto, and everything comes out a beautiful music. Every one of them is interfering with the other. Waves have the capacity of interfering. And when they interfere, they either increase or reduce in state. They either increase or reduce in state. For example, if there were to be a mob or a crowd in a particular location, or you enter into the marketplace, if you're to be speaking in a particular place and a market is introduced into that environment, your voice tends to disappear. But if you were to be speaking, if you were to be singing a song and people start joining you in that song, the voice tends to rise. So that is interference in action. We also consider what is known as polarization. Polarization actually talks about you restricting or controlling a wave and making it to work in one plane, making it to move or operate in one plane. Our transverse waves can be polarized into one plane. And how do we go about the polarization of our transverse waves? It is by using polarizers. These are, let's use light for example. You transmit your light from the source. I have a bulb inside this and I make a pinhole so that just not too much of light comes out of it. And then I want to plane polarize my light. So I have this card and I cut it vertically. Now as the wave of the light is coming, it will pass through. But if I should place something in a different plane, say horizontally now, with the same kind of cut, it will not be able to pass through. So when it passes through this first one, we say it has been plane polarized. It has been polarized in one plane. Okay, in this lesson on waves, we looked at what a wave is, and we said a wave is we discussed in this lesson on waves, we discussed on what a wave is, and we said a wave is any disturbance that passes through a medium without causing a permanent displacement on the cells or on the materials of the medium, and can transfer energy from one point to the other. We also considered wave motions. We talked about the kinds of waves. We have mechanical waves and we have the electromagnetic waves. We talked about the wave motions, and that was what we came up with: transverse and longitudinal waves. The transverse waves they move in a perpendicular direction to the originating source, while the longitudinal waves move in a parallel direction to the source of the wave. We talked about the propagation of waves. We talked about the general representation of a wave. That's how to draw the waveform. That's the graph. We talked about terminologies as amplitude, wavelength, frequency, period, velocity of the wave, even wave constant. We also talked about wavefronts, and in wavefronts we said wavefronts it simply talks about the shape or the pattern in which the wave takes when it is being generated. We talked about progressive and stationary waves. Progressive waves are moving waves, just like your light is, and stationary waves are restricted, unlike light, like a string. Wave within a spring or a string is a stationary kind of wave. We talked about the properties, characteristics of waves, and then we mentioned 4 properties. We considered reflection, that is shining back. Considered refraction, that is appearance, false appearance. We considered diffraction, that is the wave itself diffusing, trying to recover back to its original state. And we also considered interference, that is a mixing of more than one wave to get more or less. We then talked about polarization of waves, which is restricting waves to see whether they can move in both planes or they are just a single plane kind of wave. Transverse waves are planar waves. They only exist in a single when they are polarized, they can only be plane polarized. That is, they can only be polarized along one plane. I haven't spoken about all these things under waves. Some questions will come up on your screen in a few seconds. You are expected to answer them. And if there is anything that you do not understand in the course of watching this video the first time, you can watch it over again. Thank you.